Hello everyone, this video is going to be very interesting. On screen, you can see a dashboard that I have built. This dashboard is for my own load balancer that I have built myself. We will see how a load balancer works practically, and then we will break the load balancer using 4 different ways, which will teach us 4 important properties that a load balancer must have. So let's start learning about load balancer. So each one of you must already know what a load balancer is, but still I will introduce it quickly. Suppose you have multiple app servers on which client requests are expected to land. In between of client and these servers, we keep a machine whose only job is to redirect the request coming to it to one of these app servers running. This machine decides for every single request that comes in, which server should handle it. This machine is responsible for distributing the requests evenly to all the servers so that no single server feels overwhelmed by the loads of requests received from client. This machine here is known as the load balancer. This machine here distributes loads on servers using various algorithms. Now, one of the most common algorithm is round robin algorithm. Let's see this algorithm in action. I will start 4 different backend processes or app servers on different ports starting from 4001 to 4004. Right? So let's go and start it. Here, using this command, we have started 4 backend servers. Now I'll go ahead and start my load balancer. So using this command, I have started my load balancer, and by default my load balancer strategy is round robin. All the health checks are off, sticky sessions off, circuit breaker off. What are these things? We'll see later. But for now, this is the simplest possible algorithm, which is round robin algorithm. Now I will go ahead and hit this load balancer on port 3000 with different requests. And then we will see how these request counts increase when I go ahead and hit the request. So let's do that. So let's hit this simple request and see, right? So the first request has gone to first server. What about second request? Second request has gone to second one. Third has gone to third one. Fourth request has gone to fourth one. What about fifth request? Fifth request has gone to the first one, right? And so on. If we keep on hitting it, we'll see the request move on in round robin fashion, right? It works perfectly, right? Even distribution. But it is exactly where the real problem starts. Now let's try to break this load balancer in the first way and understand the first property that a load balancer should have. For our first break, what we will do is, we'll make one of the backends slow. So we'll make this backend running on port 4002 slow. So instead of responding back in 6 millisecond or 2 to 3 millisecond, we will manipulate this backend to return response every 2000 milliseconds. Remember, we have just made this backend slow like it's stuck on a bad database query. So let's run our command and make this backend slow. Okay. So we'll run this command. This command means backend running at 4002 will become slow for 60,000 milliseconds, and each request will take 2000 milliseconds to complete, right? We'll go ahead and make this slow. Now let's bombard our load balancer with lots of requests using another command. It's saying bombard our load balancer with lots of requests using 5 threads for 15,000 milliseconds. Right? Let's go ahead and run it. Now when I go ahead and send this multiple request, you watch backend 4002's bar. Let's go ahead and hit it again. First make the backend server slow and then hit it again. Right? There it goes. The graph keeps on climbing and not coming back down. The other 3 graphs are basically flat. The graph of second backend server climbed because this backend was returning responses every 2000 milliseconds. So other requests were getting piled up in the queue and were waiting for the previous request to be completed. So number of active connections as well increased, right? But watch closely on the number of requests that each of the backend server has received. Backend 4002 got the exact same number of requests as everyone else. So the round robin algorithm doesn't know or care that the backend 2 takes 1,000 times longer to respond. Round robin just knows whose turn it is and redirects the request to that particular backend. However, ideally what should happen? Ideally, this should not have been the case. Ideally, if backend 2 is taking 1,000 times more to respond, then the load balancer should be smart enough to redirect more requests to the other fast backend servers, that is backend 1, 3 and 4, and less requests to the slower one, which is backend 2. So to solve this problem, we have another algorithm known as least connections algorithm. This algorithm basically skips whichever backend is taking more time to respond and redirects the request to other fast backends. Now let's see this algorithm in action. Before that, I will go ahead and restart my backends, restart my load balancer and change the load balancer strategy from round robin to least connections. Instead of starting like this, we'll go ahead and start our load balancer using this command. Start load balancer with strategy least connections, right? Let's go ahead and start it. Now you can see on dashboard the strategy is least connections. Now let's do the same thing. Let's go ahead and make this backend too slow and hit lots of requests and see what the output is. So for making it slow, we will again run this command. Now what you see? Now you can see the same slow backend, but now its request count barely moves, right? Therefore, least connection algorithm balances the actual load, right? If you see, since this server was slow with average latency of around 2000 milliseconds, therefore the number of requests it received was only 8, right? So the first property that a load balancer should have is it should know the slow servers and redirect traffic accordingly, right? Now let's break our load balancer in second way and see the second property that a load balancer must possess. Let's reset the load balancer first to round robin. So we'll restart the servers. We'll go ahead and restart the load balancer. Now strategy is round robin. Now what we'll do? This time we'll just kill one of the backend servers. Right? So let's kill backend 3 this time. Right? I'll go ahead and kill backend 3. And after this, let's again go and bombard our load balancer with lots of requests, right? Let's see. Right, now what you see? What's the error rate here and here as well, right? All the requests landing on this backend 3 are failing, right? And the error rate is around 25%. Why? This is because 1 in every 4 requests are failing. It is because our load balancer was never told to check if a backend is actually there and up and running, right? So to resolve this, we have something called as health checks. So let's go ahead and switch on our health check and then see how our load balancer performs. We'll be using this command. Let's understand the parameter in this command. This says in our load balancer, switch on the health checks. Health interval is 2000 millisecond. That means load balancer will proactively ping each backend server after every 2 seconds and see if that server is healthy or not, right? And this is a threshold. This means if a backend server gives consecutive 3 failed pings, that means this backend will be rejected in our round robin algorithm and none of the requests will go through that particular backend, right? So we have switched on the health check. You can see health check is on, strategy is round robin. Let's go ahead and kill our server, right? And then hit lots of requests, right? You'll see, right? What you saw here. You observed that it took a few failed pings and after that load balancer realized that backend 3 is down and thus it has turned off all the traffic from it. So all the requests are going through backend 1, 2 and 4. Few of the requests did go through backend 3, but then load balancer realized none of the response is returned and therefore no more requests were passed to this backend. So second property is load balancer should be able to identify the dead server and stop redirecting requests to that server. Correct? This is the second property. Now let's break our load balancer in third way. Before that, let's restart everything. Now this one is different. This is about where the data lives, not how fast things can go in the load balancer. So what I'll do is, I will log in using one user and round robin sends the login request to say first backend, right? So this backend will store the session in its own memory, own server, nowhere else, right? And when the same user will hit request to backend 2, 3 and 4, then that user will get logged out as a response. You will see this behavior in the logs here, right? So I'll go ahead and clear the logs first. What we will do, let's log in using one of the users. So let's use this command. What it is saying is, it will log in and try to hit 6 requests. One of the backend servers, whichever gets the first request, will go ahead and save that client session, and then we'll see what the output is. Let's go ahead and enter. Right? So what do we see here? In output, we see logged out, logged out, logged out, still logged in, logged out, logged out. Here, nothing has crashed. Every backend here is telling the truth. So where has the session been stored? Session has been stored in the first backend, right? But still, the logged in user is getting logged out messages. Why? Because load balancer is distributing the load equally without caring about which logged in user has sent that particular request. So the problem is, logged in user is getting logged out messages for requests which are not actually going to the server where its session has already been stored. So to resolve this, we switch on something called as sticky sessions, right? Switching on sticky session means all the requests for a certain user will go to the same backend server where the session is stored. Let's go ahead and switch on the sticky sessions. That sticky session is on, right? Let's go ahead and enter it. Our sticky session is on, strategy is round robin and health checks are also on. Now let's go ahead and hit our load balancer with requests. Now what will happen? There was one client whose data was first stored on backend 1, and post that all the requests which belong to that particular client went on to the first backend server itself. So first backend server has 7 requests and all other backend has 0 requests, right? And this is what we want. So the third property is your load balancer should be smart enough to redirect a specific user's request to a specific backend whenever needed. However, the downside of this is, if the backend server storing the session goes down, then user session is lost, right? So the real fix here isn't the load balancer setting at all, but rather you should move the session out of these backends into something every backend can read. So a common or global cache which every backend can read is the best you can do for session store. So if you have a good architecture, then your load balancer will not be responsible for handling sticky session responsibility. Correct? Now let's break our load balancer in fourth way. This is the last one and the one that should genuinely worry you in production. First, let's go ahead and restart these servers. Restart our load balancer simply with just round robin with everything off. Now let's go ahead and make our second server slow, which we did, and then run our command, load command. One more thing, instead of making this server slow only for 2000 milliseconds, we'll make it slow for 5000 milliseconds, right? And then let's go ahead and run our load generator with 10 concurrent threads. Now let's see what happens. Here, watch the logs carefully. Here you can see 0 per second, 0 per second, OK equals to 0 per second. What it means? It means in this 1 second window, 0 request came back. That means no request finished at this particular moment. And there were 4 such seconds, and then 31 requests were fulfilled, and then again 4 such seconds were present. Now, why is this happening? Is it because all our other backends are down? No, they are perfectly healthy but idle. It is because our second backend server is so slow that load balancer never gives up waiting on this second server. Now, one by one, every worker threads that we have spawned gets stuck on this backend too, and therefore nobody is left to talk to the healthy ones. And therefore, during these 4 seconds, none of the requests were fulfilled. So one misbehaving node just quietly took the whole system hostage, right? Now, two things can fix this. The first is timeout. That is, you should introduce a timeout and tell the load balancer to stop waiting for response after some threshold. For example, after 500 millisecond, if there is no response, then just move on to the other backend server, right? And second thing is a circuit breaker. What is a circuit breaker? After a couple of failures, stop even trying this backend for a while. After some time, no request will go to this backend. We will go ahead and hit other backends. And after certain intervals of time, we will go ahead and hit backend 2 and see if this backend's latency has decreased or not. If not, we still ignore it. And if it has actually decreased, then we go ahead and start sending request back to backend 2. Right? So for this, let's go ahead and switch on our circuit breaker. So here our new command will be this, right? Now what this command states? So this command says the circuit breaker config is on, right? The timeout is set to 500 milliseconds with some failure threshold. That means after these many units of request fail to give response within the 500 milliseconds, then avoid sending request to that backend anymore. And after every 5000 milliseconds, go ahead and check if the server is returning fast responses or not. If yes, then start sending request, and if no, then keep the circuit open and do not send any request to that particular backend, right? So we'll go ahead and start our load balancer with circuit breaker on. You can see on dashboard here as well, our circuit breaker is on. Then let's go ahead and make our second server slow. Make second server slow and then put a lots of requests there, right? We can see, right? After certain number of time, after certain request fails, our backend has marked this as circuit open and no more requests are going here. Every 5000 milliseconds, circuit is half open. That means our load balancer is checking whether this backend has started returning fast responses or not. Since this backend is still not returning fast responses, therefore the circuit is still open. Now let's do one thing. Let's make this server slow. Let's go ahead and hit request for 1 minute. For 1 minute, I will go ahead and hit the request. Right? So this will be working. Meanwhile, in separate tab, what I'll do? I'll go ahead and mark this particular backend as unslowed, right? So let's mark it before our 1 minute gets over. If we mark this as unslow, what will happen? After 5000 milliseconds, again load balancer hit this particular backend. It saw that it is not slow anymore. The average latency has decreased to 2 milliseconds, and therefore the circuit was closed and this backend as well started receiving all the requests, right? So this is the fourth property that your load balancer should have. So all the 4 properties that we saw in this demonstration is very important. But a production load balancer handles a handful of other properties as well. And those properties are worth knowing that they exist even if we didn't demo it here. So the other 4 properties are TLS termination, rate limiting, connection draining, and observability. What these property states are written here, right? Also, we used only two algorithms today, round robin and least connections. But there are other algorithms as well which are worth knowing that they exist. But which one you pick depends entirely on your situation. So the other popular algorithms are weighted round robin, IP hash or consistent hashing based distribution, and the third is geographic or DNS based load balancer, right? Now the last and the most important question. The load balancer itself was built so that it can distribute loads to multiple app servers. But the load balancer itself is a single server. Won't the load balancer itself get overwhelmed by the number of requests it is receiving? The answer is it won't get overwhelmed. Why? Because of three reasons. First is its job is cheap. Round robin or least connections, a single health checkup, lookup, all of that is microseconds of CPU work compared to the actual app logic on the backends. So load balancer's sole responsibility is to take a request and route it to a particular backend. Therefore, no application logic is performed here. That is why its work is very lightweight. Second reason is, and the second reason is actually part of our own demo that we actually proved without planning it. So a load balancer doesn't need a dedicated thread for every request it's waiting on. Our load balancer was built on Node, which handles thousands of connections concurrently on a single thread, because waiting for a backend to respond doesn't block that thread. It just parks a lightweight callback and moves on to the next request, right? So because of callback also, the load balancer becomes very fast. Now the third thing is, at real scale, the load balancer itself is not even one machine. You run several load balancer instances behind the DNS so that client requests are distributed among load balancers itself, right? So this was all about load balancers. I hope you understand what a load balancer is, how it works, what are the properties that are associated with the load balancer, with the dashboard that I created and actual load balancer that I created, right? So that's it for this video. Until the next video, stay safe, stay healthy. Bye bye.